Hello students, let us continue with the current electricity level 1, lecture 2. In the last lecture, we did MCQ which were mostly related with the Weston bridge. Today we will see the MCQ related to the divisions of current as well as the Kirchhoff's law. Also, you can download the PDF file of the questions from the link given in the description of the video. Let us start with MCQ number 1. Again, a circuit is given having a total current of 3 ampere, which is the total current in the circuit. This current is divided at this junction. So the current division, let this current be I1 and this current be I2 and this current be named as total current. Say we can derive the formula for the coming MCQ. So before we find out the solution for this MCQ, we derive the formula for the division of the current when the two resistors are connected in a parallel combination, and then we will come to this question. In this question, you have to find out the ratio of the current in 3 ohms and the 1 ohm resistance. Now, before that, we do some theoretical portion and find out a formula. So here, capital I is the total current and I1 and I2 is the current in R1 and R2. Let us name this resistance as R. So name is in our hand. You can name any thing to this resistance, whether R1, R dash, anything. Now suppose I want to find out the division of this current, that is I1 and I2. Now I know that R1 is in parallel combination to the R2. So R1 and R2 are in parallel combination, and we know that in parallel combination the potential difference across these two resistors will be same. So I can write V1 is equal to V2, where V1 is the potential difference across R1 and V2 is potential difference across R2. Now this can be written as the product of the current and the resistance, that is I1 R1, I2 R2, that is a Ohm's law. Therefore, I1 upon I2 is equal to R2 upon R1. Therefore, I1 plus I2 upon I2 can be written as R2 plus R1 upon R1. That is a componendo, or simply you say that denominator is added to this numerator. So same process is done on the other side. So that is the componendo method for mathematics. Now from the junction rule, also we know that I is equal to I1 plus I2. So we replace this I1 plus I2 by I. So this is equal to R1 plus R2 upon R1. So therefore I2 is equal to total current R1 divided by R1 plus R2. So this is how we can directly find out the current in the second branch if we know the total current and the respective resistance. So it can be learned like this, that current in this resistance is equal to total current, the resistance of other, because say the division of the current will follow, or the current will follow a path which have a minimum resistance. So when the total current come at this junction, it will follow the rule, or it will follow the path where the resistance is least. So in the question, when we are trying to find out I2, we take a resistance of the other branch. So it can be learned like this: total current दूसरे का resistance divided by total resistance. So here I did the componendo on the numerator. I can do the componendo, means I can do the summation in the denominator also, and if I do this, so I can find out similarly I1 will be equal to total current, दूसरे का resistance that is R2 upon R1 plus R2. So in the coming days you can directly apply this formula whenever you need it for the division of the current in the parallel combination. Now let us come to our question. We have to find out the ratio of the current in 3 ohm resistance and 1 ohm resistance. Means we have to find out I1 upon I. I1 upon I. In the following figure, the ratio of the current in 3 ohms and 1 ohm resistance is, so total current we know it is 3 ampere. I want to find out I1, so I can use this formula, total current 3 into resistance of other, that is 6, divided by total resistance, that is 9. So 3, 3, 9 and this 2. So this is 2 ampere. So out of this 3 ampere, 2 amperes flow through this resistance, so remaining 1 ampere will flow through this. We want to find out the ratio of I1 to total I. So I1 is 2 ampere and total is 3. So the ratio is 2 by 3, that is option number B. So you can remember this two formula, that is a division of the current when two resistors are connected in a parallel combination. Now let us see the second MCQ, where we have how will the reading in the ammeter A of the figure be affected if another identical bulb Q is connected in parallel to P as shown. The voltage in the main is maintained at constant value. So we have two bulb or a resistance. One is marked as P and we have an ammeter at this point. Then we have a key at this point and the other identical bulb is connected at this point. This is named as Q. The voltage at this end is maintained constant, that is, let us name this voltage, input voltage, as a V0. So the question is, when we switch off or when this switch is on, that is the circuit is completed, how the reading of the ammeter will be affected. We know the ammeter will show the current. So when the switch is open, that is the first situation, let us name their let us say the resistance of this bulb is R and this is also identical bulb. So its resistance will also be R. So when switch is open, so no current will be flowing through Q. The entire current will be flowing through P. So the total current in the circuit will be equal to total voltage divided by total resistance. This is the situation. Now, when the switch is closed, so as soon as we close this switch, both the resistance are in parallel combination. So R equivalent becomes R by 2. Clearly, the current is reduced by 2, or the new resistance becomes half of the original. So as the resistance decreases, the current in the circuit should increase. So I dash will be equal to, again both are in parallel combination, so voltage is same, divided by R equivalent, that is equal to twice V0 upon R. So this is your I, so it becomes twice I. So let us say the option given, the first is the reading will be reduced to 1/2, so that is wrong. So clearly the answer should be the reading will be double of the previous one, so current is doubled, that is option number B. So the correct option is B in the circuit. Now let us come to this question number 3. Again, we have a diagram where different resistance are connected in the different arms. So this is point B, this is point A. Let the current is I1, R1, O or 0 is the origin. This is another resistance C named as R3. The current is coming to this point I2, I3, and the fourth arm is D. This is I4. Let the resistance is R4. So this is the diagram which is given to us, and we have to find out what is the potential at the junction O or the junction 0. So we have to find out the potential at junction. So all the values are given. R1 is 10 ohms. So R1 is equal to 10 ohms. R2 value is also given, that is 20 ohms. R3 value is equal to 40 ohms. Then R4 is equal to 80 ohms. So these four resistance are given. As well, we have the potential at point A, B, C and D is also given. So potential at point A is equal to 5 volt. Potential at point B is equal to 10 volt. Potential at C is equal to 20 volt. Potential at D is equal to 15 volt. Find out the current in the resistance R1. Now say that in the option it is given that a current is flowing towards A or away from A. So it means the direction of the current given in the question is not correct. We don't know whether the potential at point A is more or the potential at O is known. So here you have to find out the current in this resistance, not the potential. But we can find out the direction of the current only when we know which point is at a high potential and which point is at a low potential. Then only we will be able to, so if A point is at high potential and the O or 0 point it has low potential, then the current will flow from A to O. And if O point is at high potential as compared to A, the current will flow in the opposite direction. So first we have to find out what is the potential at this junction, because when the potential is known at this point, then and only then we will be able to determine the correct direction of the currents. Now, first thing is, we know that from the Kirchhoff first law, the algebraic sum of electric current at the junction is 0. So from the diagram we know that whatever be the direction of the current at the junction, the current is 0, that is charge can neither be created nor destroyed, neither they get accumulate or stop anywhere in the circuit or at the junction. So the another form of the Kirchhoff first law, that is KFL, I am writing summation of I is equal to 0. This is another form, and sometimes we directly use the current approaching the junction is equal to the current leaving the junction, that we did in our theory. Now algebraic sum of the current at the junction is 0. We don't know what is the direction, that we have to find out. However, I1 plus I2 plus I3 plus I4 is equal to 0. That is equation number 1. Now, see the situation. If we can find out the direction, the potential at the junction, it will be very easy to determine the direction of I1, I2 or I3. Suppose I apply the Kirchhoff law from point A to O only. So if I apply the Kirchhoff law from point A, it will be VA minus I1 R1 is equal to V0. So this will be the situation. We are moving in the direction of the current. If we take the direction of the current to be correct, then this should be the equation. So in this situation, we can write minus I1 R1 is equal to V0 minus VA. This can be the situation. Then, if I apply the Kirchhoff law, we assume that we are taking the direction of the current given as correct. Suppose I apply, this is the Kirchhoff law applied from point A to R1 to O. Similarly, if I apply the Kirchhoff second law from point B to R2, let us this name this R2, and again at junction O, then it becomes VB minus I2 R2 is equal to again V0. So minus I2 R2 is equal to V0 minus VB. This will be the situation. We are assuming that all the current given, the direction of the current given is correct. But if we know the potential at point O, then we can find out the correct direction. So see, similarly, if you try to apply the Kirchhoff second law from C to O, you will get I3 R3 minus I3 R3 is equal to V0 minus IP. Now I know I1 plus I2 plus I3 plus I4 should be 0. So I can find out I1 from this point, I2 from this point. All are identicals. The equation is identical. Identical means in the sense this about the sign. About the plus and minus sign. So in the place of I1, I can write V0 minus VA upon R1. Now because we will get a minus sign, I have not written this for C and D. You can write the equation from R, C to R3 to O and D to R4 to O. All will be the identical. So minus is taken as common because here we have a 0. So it does not make any difference whether I write here plus minus. First I need to find out the potential at the junction. So V0 minus VA upon R1, then plus V0 minus VB upon R2 plus V0 minus VC upon R3 plus V0 minus V0 D upon R4, all is equal to 0. So this is using equation 1. Using equation 1 and the minus is taken common. Now we know the values of R1, R2, R3, R4, VA, VB, VC and VD. So only the unknown is V0. So let us substitute this value. So it becomes V0 minus 5 upon 10 plus V0 minus 10 upon 20 plus V0 minus 20 divided by 40 plus V0 minus 15 upon 80 is equal to 0. So we take the LCM to be 80. So it becomes 8 times V0 minus 5 plus 4 times V0 minus 10 plus 2 times V0 minus 20 plus V0 minus 15 equal to 0. So now there is a simple calculation. This 80 is gone to that side, that becomes 0. So 8 V0 plus 4 V0 plus 2 V0 plus V0. So 8 plus 4 12, 12 plus 2 14 plus 1 15 V0. Then we open the bracket, this becomes minus 40. Then here we have again, 8 5 is 40, okay, minus 40. Then here again we have minus 40. Then we have minus 15. So it becomes minus 135. It becomes minus 135. So minus 135 is equal to 0. So you can do this calculation. You can open this bracket. So 15 V naught is equal to 135 and V naught is equal to 135 upon 15. So that is equal to 9 volt. So clearly the potential at this point is 9 volt. Now it is clear that a potential at point A, which is 5 volt, is less. So this direction of the current should be away from, so in the option they have given whether it is towards O or away from O. So it should be away from O since V naught is greater. So that direction we can find out. We need to find out the value of I1 also. So we use this equation. Let us name this equation as 2. So using equation number 2, so if I use equation number 2, VA, that is 5 minus I1 multiplied by 10 is equal to 9. So therefore 5 to this side, so minus 10 I1 is equal to 4. So I1 is equal to, so I1 is equal to minus 4 upon 10. So I1 is equal to minus 0.4 ampere. Now see, when we discuss this theory, so it is 0.4 ampere, but here we got the answer to be minus 0.4 ampere. So what does it mean? That whatever direction we have considered, that is not correct. The current is flowing in the opposite direction. So here negative sign indicates the direction because you know that a current is a scalar quantity. So I have taken, while applying this law, we have taken the current direction to be same. But when we try to find out the values, the current value comes out to be minus for this I1. Similarly, when you take, suppose now B point is 10 volt. So this is 10 volt, this is 9 volt. So if I use this equation, see, let you use this equation. So VB is equal to 10 volt minus R2 is 20 I2, that is equal to 9. This is equal to 9. So again the current direction comes out to be positive. So it is minus 20 I2 is equal to minus 1. So I2 is equal to 1 by 20 ampere. So here the current direction is correct. Then I3, so you see the potential is 20 volt and this is 9 volt. So again that I3 will come out to be correct, that is positive. This is 15, this is 9. But it is not the case with I1. So I1 is minus 0.4 ampere. So minus sign indicate the direction. So the correct answer should be 0.4 ampere away from the junction O, means the current should flow in the opposite direction. So the option given here is again B option. So this is how we determine the direction of the currents. Now see MCQ number 4. We have 4 different batteries. The name of the batteries or the cell are EFGH, having 2 volt, 1 volt, then the EMF of this is 3 volt and that of H battery is 1 volt. We have to find out the potential difference between point B and D, where the resistance, let us name this resistance as capital R, that is 2 ohms. All the cells have the internal resistance. So in the given diagram, they have not drawn the internal resistance. So we have drawn an internal resistance kept in a box. We have named this internal resistance. So while applying the Kirchhoff law, we can easily determine its value. So the question is, first is calculate the potential difference between point B and D. So we have to find out the potential difference between point B and D. Now let us name this battery. Let us name this battery as E3 because we named this R3. Let us name this battery as E4, this battery as E1, and this battery as E2. Now clearly there are 4 cells or 4 batteries. So we will start distribution of the current. We don't know which points are at a high potential or low potential, whether the current will flow from point B to D or D to B. So we don't have to worry about that. The Kirchhoff law will take the care of that directions. We simply start our distribution from the cell which have a largest EMF or which have a large value of EMF. So out of these 4 cells, the cell G has 3 volt EMF. So we start our distribution from this terminal. Let the current flowing or the current from this cell is I. So this I will come to the junction B. Then at B there is a division of the current. Let us name this current as I1. So the remaining current that will flow through this battery E1 is I minus I1. That same current will flow through this F cell. When this current comes at this point D, that I1 will come here, and again the same current. So I1 approach D. From A, the current approaching is I minus I1. So when we do the resultant Kirchhoff first law at point D, the total again will become I. So whatever amount of current we start at, that amount of current come back to the same cell. So the distribution is done properly. So to find out the potential difference between point B and D, we should determine the I1 value. Now in this circuit or in this distribution, there are 2 unknowns. That is, one is I and other is I1. So at least we need the 2 loops to determine this values. So we have these 2 loops. One loop is taken like this and another loop is taken like this. You can take an entire loop also. You need 2 equations because we have 2 unknown. So applying Kirchhoff second law to loop, let us start the loop with D. So D, E3, C, E4, B, R, and again D. So this is the loop direction we have taken. So starting from this point D, you are moving in the direction of the current. So minus IR3. Then we come across the negative terminal. So minus E3. Then again you are moving in the direction of this current. So minus IR4. We come across a positive terminal. So plus E4. Then you are again moving in the direction of current, that is minus I1R. So when you are moving in the direction of the current, the potential difference is negative, and whichever terminal we first come across, we put that sign. Substituting this value, R3 value. So R3 value is 3 ohms. So whatever is the value of their EMF, that is the value of their EMF. So R3 given is 3 ohms. So minus 3I minus R4 value is 1 volt. So minus 1, that is minus I into 2I1, that is equal to, this is minus 3 plus 1 volt. So therefore we have minus 4I minus 2I1 is equal to minus 2. So this is one equation, or we divide it by minus 2 on both the sides. So we get 2I plus I1 is equal to 1. Let us name this equation 2. We may need this equation also. So we have numbered that also. Now applying Kirchhoff's second law to loop. Now let us take this loop. So we start again with D, capital R, B, E1, then A, E2 and D. So again we start from D to this point R to B. So current is coming from opposite side. So we take I1 R plus sign. Then you are moving in the direction of the current. Now this have a current I minus I1. So you are moving in the direction of current. So minus I minus R1, I minus R1. Again you are, then we come across the negative terminal, so we put equal sign minus E1. Then you are moving in the direction of current, you come across the plus terminal, so plus E2. You are moving in the direction of current I2, I minus I1. Now we substitute these values. So we have 2I1 minus R1 value is 2, so minus 2I minus I1 minus R2. R2 is 1 volt, so minus 1 is equal to, again we have minus 2 plus 1. So therefore 2I1, both are identical terms, so like term, so minus 3I minus I1 is equal to minus. So we have a mathematical calculation only. Therefore, so 2I1 minus 3I plus 3I1 is equal to minus I1. This is equal to 5I2 minus 3I is equal to minus 1. Sorry, this is 5I1 minus 3I is equal to minus 1. So let us name this, or if we change the polarity of this equation also, it becomes 3I minus 5I1 is equal to 1. Let us name this equation number 3. Now see, we need to find out I1. So now we have two equations, this equation number 2 and equation number 3. We don't want to eliminate I1, so we will try to eliminate this I. So directly you can find out the answer of I1. Otherwise you eliminate I1 and find I first and then I1. Anyhow, we multiply this equation 2 by 3, so we get 6I plus 3I1 is equal to 3. Then equation 3 by 2, so it becomes 6I minus 10I1 is equal to 2, and we do the subtraction. So minus plus minus, so 6I minus 6I, then 3I minus 1 minus of minus I1, it becomes plus, so it becomes 31I, and that is equal to 1. That is 3 minus 2. So we subtract this value and we find I1 to be 1 by 13 ampere. Similarly, so this is I1 is equal to 1 by 13 ampere. This is your I1. Now we need to find out the potential difference between B and D. So we move from, again applying Kirchhoff's second law to path. Now it is an open path. So we apply Kirchhoff's second law from point B, R to D. So we start with B. Therefore VB in the direction of the current. So minus I1R, and we stop at D. So that is VD. So we want to find out potential difference between point B and D. So VB minus VD is equal to I1R. So VBD is equal to, I1 is 1 by 13 multiplied by 2. So we have 2 by 13 volt. So this is the potential difference between point B and D. So that is option A for the first part. That is option A for the first part. However, in the question we have two parts. Second part is find the potential difference across the terminal of each cell G and H. You have to find out the potential difference across the terminal across the cell G and H. But in the option, we have only one part. So there is some mistake in this MCQ. We have the option given for the first part only. But in the question, we have a second part. You have to find out the potential difference or terminal potential difference across G. So you see this G, this is the G portion. So terminal potential difference will be between point D and C. See here we got VBD or I1 to be positive. We got I1 to be 1 by 13 ampere. It means the direction of the current what we have taken is correct. However, it may be possible that you may get I1 sometime a negative, not in this question. So if you do the distribution in any way, I started with this 3-volt battery. It is not necessary to start with the battery. You can start from anywhere because both the laws obey the law of conservation of the charge. That first law obey the law of conservation of charge and the second law obey law of conservation of energy. So charge will be constant, the energy will be constant. So I may start from this point, say 1 volt, and I can do the distribution. Suppose I did the distribution in the opposite direction. So I will get a current in this branch to be negative. It means our whatever direction we have taken, the answer should be opposite of that. However, if we start with a battery having a large EMF, there will be no such questions of plus and minus. Now, I have to find out the terminal potential difference across G. So I can again apply the Kirchhoff law from point D, then cell G, and then point C. So I start with D, so VD. I am moving in the direction of the current. So it becomes minus IR3. Then we come across this negative terminal, that is minus E3, and plus we stop at C point. So here you need I value also. So to continue the second part, I1 we obtain 1 by 13 ampere. So from this equation we know 2I will be equal to 1 minus I1, that is 1 minus 1 by 13, that is equal to 12 by 13, 2I. So I will be equal to 6 upon 13 ampere. So this will be the total current in the circuit, that is 6 by 13 ampere. So we substitute this value VD minus 6 by 13 into R3, that is 3 ohms only, is equal to minus 3 plus VC. So therefore VD is VD minus 18 by 13 is equal to minus 3 plus VC. So VD minus VC is equal to minus 3 plus 18 by 30. So that will be equal to minus 39 plus 18 upon 30. VD minus VC will be equal to minus 39, that is 13 3s are 3 3s are 13 3s are, so 939. So minus 39 plus 18. So minus 39 plus 18 divided by 30. So this is equal to minus 21 by 13 volt. So clearly minus sign indicate that VD is less than VC, and from the diagram also it is clear that the positive terminal is connected to point C. So VC point is greater than VD. So VC minus VD is equal to minus 21. So I can write like this: VCD is equal to 21 by 13. That is equal to 13 1 ja. So 7 8 81.6 something. So you can find out this value. So this is the terminal potential difference. So here I applied the Kirchhoff's second law, and we also know that the terminal potential difference is equal to the EMF minus I of R. So for this case, for this battery, what is the EMF? 3 volt minus what is the I? We obtained I to be 6 by 13 into internal resistance, that is 3. So again, if you see this you will get 33 is 39 minus 18 by 13. See, we have a same value, but now there should not be any confusion about this negative sign. So you can directly apply the terminal potential difference formula also. So similarly, you can find out the terminal potential difference across H. So terminal potential difference across H will be equal to its EMF. So the terminal potential difference here, it was E4 minus I current was flowing. So I into R4. Here you can write E3 I upon R3. So what is E4? 1 volt minus I 6 by 13. R4, that is 1 only. So that is 13. E4 is 1 volt minus 6 by 13. R4 is 1. So it becomes 13 minus 6, 7 by 13. So the terminal potential difference across H will be equal to 7 upon 13. So see, if we directly apply this formula, what we did here, now see what is the common mistake in such type of MCQ. Here there was no problem, you will get a, however the options are not given, but even if the options are given, many students make the mistake at this point. So we tried to find out the terminal potential difference, one directly by the formula, and other I have rubbed this portion. I applied the Kirchhoff law from point D to E3 to point C, and I have written VD like this, VD minus I R3 negative terminal first, so minus E3 plus VC, and we found that this was a negative term. And terminal potential difference, so the answer was same in this both the cases. But what is error for this? Suppose I apply the Kirchhoff law from C to B, say C to E4 to B, so VC in the direction of current minus I R4. I come across positive terminal, so plus 1, and then VB plus VB. So VC minus I is 6 by 13, R4 is 1, so it becomes 1 plus VB. So VC minus VB is equal to 1 plus 6 by 13, that is equal to 13 plus 1, 13 plus 6, 19 by 13, that is 1.60, so 1.4 something. So see, if I directly apply the formula, I get 7 by 13, and if I apply the Kirchhoff second law, I get different answer. But in this situation, if I apply the Kirchhoff second law or a terminal potential difference, I get the same answer. Here I got VD minus VC was equal to minus 21 by 13. Here terminal potential difference VCD. So if I interchange this, I got the same answer, that is 21 by 13. So what is the error in our calculation? See, the current is coming out from the positive terminal. So this is the case of the discharge of a battery, and here you see the current is entering from the positive terminal. And while doing the theory, we discussed that if you are taking a current from a cell or a battery, the battery is been getting discharged, and if you are giving the current to the battery is charged. So this is the charging case, and in the charging case, you know you have to apply this formula as plus sign. So here it should be plus, so there should not be any confusion regarding this two different formula. So if the cell is discharging, you put a minus sign, and if the cell is charging, you put a plus sign. Otherwise, the safe side is apply the Kirchhoff's second law to the open path. You start from one point and stop at another point, whichever. If you get a positive answer, then C potential is greater than B potential, else the opposite thing. So you can do this. Otherwise, you remember charging and discharging, the current is drawn. So discharging, current is given. Charging, again see, the current is coming out from positive terminal. This is discharging. Current is going in from the positive terminal. Again it is charging. So discharging, charging, this is discharging and this is charging. So you can find out the respective potential difference. So we wind up our lecture at this point. You can practice the other or the remaining MCQ, which we will discuss in the next lecture. Have a nice day.